Today we learn sequence in R. Let R be a real number system and A be a subset of R subset of R. Then a map F from N to A. Where N is a set of natural numbers is a set of natural number. Is called sequence in A. What we have? Let R be a real number system and A be a subset of R. Then a map F from N to A, where N is a set of natural number, is called a sequence in A. If we represent F from N to R, then we may write F is a sequence in R. Still, when A is a subset of R, it is still F is still a sequence in R. Actually, this contain real numbers. So what we have? We have a set N. You know, N contain 1, 2, 3, N and many more numbers. They are the natural numbers. And here we have a set A, suppose. What is A? A is a subset of R. So then one maps, or this is a map F. So one map somewhere here, some point here, two maps here, three maps here. And what this point represent? This element represent F1. If we say this is F2, that is image of 2. This is first element is image of F1, and this is F3. And similarly, N map on an element that is Fn. Okay, if we represent F1 by A1, F2 by A2, F3 by A3, and in the similar manner, F4 by A4 and Fn by An. Then we denote F, or we may write F as An. N belongs to N, or as A1, A2, A3, this one. So this is called An. This is called sequence in R. Actually, A1, A2, A3, An is a sequence in R. So what is sequence? Sequence is actually a map. So how a map represents a sequence, that is clear to you. I hope it is clear to you now. Next we take some example. Let F from N to R be defined by Fn equal to 1 for each N belongs to n. It means what else? We have f1 is 1, f2 is 1, f3 is 1 and fn is 1. So in this way, our sequence is 1, 1, 1, 1, 1. Since each term is 1, so this is a f is a constant sequence. This is actually a constant sequence. Or what will be the nth term of the sequence? Nth term is n. Nth term fn is 1. So this is the first example. Next we take another example. The map f from n to r defined by fn as 1 if n is odd and -1 if n is even. So this f defined by this is a sequence in R. Like here, fn defined by this, you may complete the sentence again here, is a sequence in R. Sequence in R. Similarly, here, this is a sequence in R. What this sequence is actually? F1 is 1 is odd, so its value is 1. What is F2? 2 is even, so its value is -1. Again, F3 is 3 is odd, so its value is 1. And F of 4, 4 is even, so its value is -1. So in this way we go on, and what will be the sequence? 1, -1, 1, -1 and so on. So this is or you may write its general term Fn as -1 raised to the power n plus 1. So this 1 -1 with nth term -1 n plus 1, this is a sequence in R. You know that you can see here the elements are oscillates between 1, -1, 1, -1, 1, -1. So actually this second one is the example of the oscillatory sequence. First one is a constant sequence and second one is the example of oscillatory sequence. Third, the map f from n to r defined by Fn is 1 upon n. N belongs to set of natural number. Is a sequence in R. Now, when we put n equal to 1, the first element is 1. When we put n equal to 2, we get 1 by 2. For n equal to 3, 1 by 3. So, in this way, nth element is 1 by n. So, we have the sequence in R. Again, next example, the map f from n to R defined by Fn as 1 minus 1 upon n. Or here n belongs to set of natural number. This map describes a sequence 0, 1 by 2, 2 by 3, 3 by 4 and so on. Similarly, if we have a map F from N to R and it is defined by Fn equal to N, then it is a sequence. So what will be the sequence here? 1, 2, 3 and so on. So these are the some examples of the sequence in R. You may I'm writing here the nth term of some sequences. So if this is an, then we may also write this like it is a sequence in R. Or we may also write an as 1 plus 1 upon n, then n belongs to n is a sequence in R. Or we may write Fn. Obviously, F is a map from set of natural number R defined by Fn equal to 1 upon n square. N belongs to set of natural number is a sequence in R. Or simply if we write 1 minus 1 0 1 minus 1, then this is again a sequence. Then if we write 0 1 2 3 3, this is again a sequence. 10, if we write 3 3 2 2 1 1 0 0, this is again a sequence. So in this way, if we write down a sequence of numbers, real numbers, which are actually images of 1 2 3 4, that is natural numbers 1 2 3 4, then the images formed a sequence in R. What actually an? An is Fn. So actually it is image of n under map F. It is not necessary that all the terms of a sequence may be distinct. For example, in this sequence, first two elements are same, next two elements are same, then 1 1 is same. So it is not necessary that the sequence have a it is not necessary that sequence have a all distinct elements. Elements may be repeated. Suppose in this sequence where all the elements are same, then this sequence is called a constant sequence. So if we write, so you know what is constant sequence. Next one is, if we write numbers like 1 2 3 4 and so on, then you can see here these numbers are in increasing order. So this is a increasing sequence. This is a increasing sequence, or it is called the strictly increasing. Strictly increasing sequence. That is an is less than an plus 1 for all n. For every natural number n, an plus 1 is greater than an. That is, each element is greater than from its previous element. If we put here the sign an less than equal to an plus 1, that means some element may be equal to its previous element, then we say this is monotonically increasing sequence. Monotonically increasing sequence. What is monotonic for example, if in the above sequence if we write 1 2 2 3 4 5 5 like this, so this element is same as its previous element and 2 is same as its previous element 2. So actually this is the example of the monotonically increasing sequence, and this is the example of the strictly increasing sequence. This is strictly increasing sequence. Similarly we have here, similarly we have decreasing sequence. So what is decreasing sequence? If we write elements in the decreasing order, so how? If we write like 1 1 by 2 1 by 3 1 by 4, you can see that all elements are decreasing. So it is again a decreasing sequence, and it is actually a strictly decreasing sequence. A strictly decreasing sequence. If any two number may be same, then this is called monotonically decreasing sequence. Suppose we write 5 4 4 3 2 1 1 0 -1 -2 -2 like this sequence. It is decreasing, but there are some elements, some terms which are same. So this is called the monotonically decreasing sequence. Decreasing sequence. So now we have a definition of these four type of sequences. A sequence n belongs to set of natural number in R. This sequence in R is said to be monotonically increasing. Or sometimes we may also say non-decreasing. If n greater than m implies an is greater than equal to am. This is a different form of writing this one monotonically. So actually here we represent one indices as m and another one is n. So if n is greater than m, then an is greater than equal to am. Obviously m and n, they represent the natural number. So again, next definition. A sequence an in R said to be the same. A sequence an said to be, here is monotonically increasing, and now we have strictly increasing. If n greater than m implies an is strictly greater than am. So this is actually this represents the whole of this. So we will put a bracket here. Similarly, a sequence in R is said to be monotonically decreasing. Decreasing or non-increasing. If n greater than m implies an less than equal to am, then this is called a monotonically decreasing sequence. And fourth one, a sequence is said to be strictly decreasing if here this portion is same. A sequence an in R is said to be. You have to write down this line in each of this definition. So a sequence an in R is said to be strictly decreasing if n greater than m implies an is less than am. So this is strictly decreasing sequence. Example, I have already given examples of these four sequences. Now again there is a definition here, and what this definition says a sequence n belongs to set of natural number in R is called a bounded above is called bounded above if there is an alpha in R such that an less than equal to alpha for all n belongs to n. That is, if each element of sequence is less than this real number alpha. Alpha is a real number, and if each element of this sequence is less than alpha, then this sequence is called bounded above. For example, if we take this sequence 1, 1 by 2, 1 by 3 and so on, then each element of this sequence an is less than equal to 1. Each element of this sequence is less than 1. So this sequence is bounded above sequence. Again, next definition is a sequence an in R is called bounded below. A sequence an in R is called bounded below if there is a beta belongs to R. It means there exists a real number in R such that an is greater than equal to beta for each n where n belongs to set of natural number. Then this sequence is called bounded below. For example, in the above sequence 1, 1 by 2, 1 by 3, you can see that these elements are reducing plus, but they all are positive and they never become 0. That is, 0 is not the element of this sequence, but you may observe that an is greater than, not equal to, it is actually greater than. An is greater than 0 for all n. So this sequence is bounded below by 0. So a sequence, next definition is, a sequence is bounded if it is bounded above as well as bounded below. So again, the example that we have, this sequence luckily have the lower bound as well as upper bound. All the elements are, all the elements an are greater than 0 and less than equal to 1 for all n. So this sequence an is bounded sequence here.